Problem is to decouple. Now the first thing is you can't always decouple. You must, to decouple, the eigenvalues must all be real. Must all be real and non-defective. In other words, if they are repeated, they must be complete. You must have enough independent eigenvectors. So they must be real and complete. If repeated, they must be complete. They must not be defective. As I told you at the time when we studied complete and incomplete, the most common case in which this occurs is when the matrix is symmetric. If the matrix is real and symmetric, then you can always decouple the system. That's a very important theorem, because particularly since many of the problems, equilibrium problems, normally lead to symmetric matrices, and they're solved by decoupling. Okay. So what are we looking for? So we're assuming this, and we need it. In general, otherwise, you cannot decouple if you have complex eigenvalues, and you cannot decouple if you have defective eigenvalues. Well, what are we looking for? We're looking for new variables. UV equals A1, B1, A2, B2 times the XY. And the question is, this matrix is called D. It's called the decoupling matrix, and it's what we're looking for. How do I choose those new variables U and V when I don't have any physical considerations to guide me as I did before? Now, the key is to look instead at what you're going to need. Remember, we're changing variables, and we're changing, I told you from the beginning, first days of the term, when you change variables, look at what you're going to need to substitute in to make the change of variables. Don't just start writing equations. What we're going to need to plug into that system and change it to the UV coordinates is not U and V in terms of X and Y. What we need is X and Y in terms of U and V to do the substitution. So what we need is the inverse of this. So I'm going to write that. So this is in order to do the substitution, what we need is X, Y. Oops, I shouldn't have called these. Let's call them prime. Okay? The real A1 and A2 is going to be, let's call these A1, because these are going to be much more important to the problem than the other ones. Okay, I should call this matrix D inverse. That would be a sensible thing to call it. Instead, since this is the important matrix, this is the one we're going to need to do the substitution, I'm going to give it another letter instead, and the letter that comes after D is E. Now, E is an excellent choice because it's also the first letter of the word eigenvector. And the point is, the matrix E which is going to work is the matrix whose columns are the two eigenvectors. The columns are the two eigenvectors. Now, even if you didn't know anything, that would be practically the only reasonable choice anybody could make. What are we looking for? We're looking for to make a linear change of variables like this really means to pick new I and j vectors. You know from the first days of 1802. What you want is a new coordinate system in the plane, and the coordinate system in the plane is determined as soon as you tell me what the new I is and what the new j is in the new system. So what you have to establish a linear change of coordinates amounts to picking two new vectors which are going to play the role of I and j instead of the old I, and the old j. Okay, so pick two vectors which somehow are important to this matrix. Well, there are only two, the eigenvectors. What else could they possibly be? So the only thing to try, now what's the relation? I say that with this, this automatically makes, what happens is, I say that alpha 1 corresponds, and alpha 2, these are vectors in the xy system. Well, if I change the coordinates to u and v in the uv system, they will correspond to the vectors 1, 0. In other words, what the vector that we would normally call I in the UV system, and this one will correspond to the vector 0, 1. Now, if you don't believe that, I'll calculate it for you. It's very easy to, the calculation is trivial. Look, what have we got? xy equals, so xy equals a1, b1, a2, b2. This is the vector, the column vector alpha 1, and this is the column vector alpha 2. Okay, now, here is u and v. Okay, suppose I make u and v equal to 1, 0. What happens to x and y? You matrix multiply. 1, 0. 1, so a1 plus 0, b1 plus 0. It corresponds to the column vector a1, b1. And in the same way, 0, 1 corresponds to a2, b2. Just by matrix multiplication. And that shows this thing, that these correspond. So in the UV system, the two eigenvectors are now called I and j.